I will. Okay, more electrical principles.
Did you want to flip the camera back around too?
Let's see. Let me stop. I can't stop recording. Make sure that's full screen. All right. Are we good now?
It looks good, thank you.
Okay. So a little more on resistors and capacitors, inductance, and how to calculate when they're in series and parallel. We'll talk about transformers, and then we'll do more coordinate systems and phasors, a little more polar coordinates, logarithmic axes. Let's see. We're way far ahead there. Okay. So if we have resistors in parallel, and we talked about this before, you do the reciprocal of the sum of the reciprocals. When they're in series, they just add. When we talk about capacitors and inductors, they work a little bit different. So in this case, what's the total resistance if we have a 10, 20, and 50 ohm resistor in parallel? So the one thing to remember is when they're in parallel for resistors, the value is going to be equal or less than the lowest value of the components. So in this case, we know the answer has got to be 10 or less. So we have to choose between 5.9 and 0.17. And if I had to guess, I think I would go with alpha. Yeah. So if we have 100 ohm and a 200 ohm in parallel, what's the value?
150 acre. Cheap on
150? You think it's Bravo?
Oh gosh, no, 79 C. Oh, yeah, too cold.
Read all the answers before you answer.
Yeah, 60 goes down for 60.
That's something that'll get you. You come to one, oh, that's right.
Oh, yeah.
And you don't read the other one. And that was not intuitively obvious. Well, you knew that it had to be less than 100.
Yeah.
But which one?
Even when it's 2, you just do 100 times 200 divided by 100 plus 200. A little easier.
That second formula that you had at the bottom there in red, am I correct? That one, if I recall right, only works for 2 parallel resistors. It does not work for 3 or more. That's where you have to use the sum of the inverses like you have on the first red line at the bottom. Is that right?
Correct. Now, if they all are equal value, you can just divide by the number. That's a special case. So if you had 3 100 ohm resistors, you'd have 33 1/3 ohms.
Mm-hmm.
If you have inductors in series, they add like resistors. And in parallel, they act like resistors where you have to do the reciprocal of the reciprocals, or the same special cases. If you had 2, you can, or they're all equal. I'm getting double clicks. Which of the following components should be added to an inductor to increase the inductance? So let's say I had
Delta.
10 microhenry inductor, and I want to get 12. What do I do?
See, put it on.
Delta.
The, in series. Well, I know there's a series with. Oh, okay.
Inductors.
They had.
In series.
It's the capacity.
What's the inductance of a circuit with a 20 millihenry inductor connected in series with a 50 millihenry inductor? You don't need a calculator for that. What's the inductance of three 10 millihenry inductors connected in parallel?
D.
Which?
D.
D.
What?
Delta? Three in parallel. 3 10s.
Oh. There's no way.
Just take your time, read the question, read the answers. All right.
The first two were wrong because of what? Because they're in the wrong value, right?
The other way, orders of magnitude.
Yeah, they're Henrys. That's
Pretty big stuff.
capacitors in series. They're the reciprocal of the reciprocals, but they add in parallel. So which of the following components should be added to a capacitor to increase the capacitance? Charlie. So you can piggyback them and increase it. That's what you do with the surface mounts. What's the capacitance of a 20 microfarad capacitor connected in series with a 50 microfarad capacitor? So we know in series it's going to be less than 20, right?
There's only one reasonable way.
Well, there's only two possible and only one reasonable.
But if I remember right, there's a way of those two that we had before. There's a way that
Product divided by the sum.
you could come up with the number, the 0.07, by multiplying something. They give you the right answer and then the incorrectly calculated.
Oh, okay. Yeah, I guess if there's a way, if you did it wrong, you could maybe come up with that other one. Okay, we have three 100 microfarads in series. No calculator required.
Delta.
Ed,
Not until I
read all four answers.
Okay, wait a minute. Oh, wait a minute. They're in series?
They're in series. In this case, it's blocked down there, but since they were all equal, you can just divide by 3. What's the equivalent capacitance of two 5 nanofarad capacitors and one 750 picofarad capacitor in parallel? So we got 3 capacitors in parallel.
nanos and picos, so what's your nanos and picos?
Well, 750 picofarads is 0.75 nanofarads. Very good. Transformer. Basically, it's 2 inductors with a common core. It could, I guess, even be air core. In most cases, it's going to be some kind of a high permeability, either like a power transformer, it's usually laminated iron to reduce the eddy currents, or it might be a toroid made with ferrite, could even be powdered iron. And it has a primary and a secondary winding. It could have multiple primaries and multiple secondaries. Usually it'll have one or more secondaries. In old tube type equipment, you would have a power transformer that would have a primary where you put 120 volts in. You'd get 6.3 volts on one side for filaments. You'd get a high voltage, maybe 400 volts for the plate voltages, and you might get 100 volts or something for screen voltages. You don't see too much of that anymore. Even in the tube type power amplifiers, are usually grounded based triodes. You'd only have one high voltage and a filament. And the primary and secondary are just convention. You normally input the primary and the secondary is the output, but you can certainly turn it around and apply voltage to the secondary and get your output on the primary. In fact, there's a question about that coming up. So an AC voltage across one of the windings, you just call it the primary, will cause a current to flow, which creates a magnetic field. And that magnetic field, as it increases, causes a voltage and a current in the other winding. It's called mutual inductance. The one thing to remember on a transformer is power in equals power out, almost, if there were no losses. You can't get any power increase through a transformer. You can increase the voltage or you can increase the current, but you don't increase the power. The turns ratio, which is the ratio of the number of turns on one winding to the other winding, will determine the voltage increase or decrease, and also the impedance transformation, because that's the square of the turns ratio. So if you had a turns ratio of 2, the impedance ratio would be 4. So why is the primary winding wire of a voltage step-up transformer usually a larger size than that of the secondary winding? So it's a case where you're increasing the voltage on the secondary, which means because power in, power out, the current has to be less on the secondary, right? So what's that say about the primary? It's going to have more current. So what causes a voltage to appear across the secondary winding when an AC voltage source is connected across its primary winding? Did you see Charlie? Okay, very good. What's the voltage output of a transformer with 500 turn primary, 1500 turn secondary, when you apply 120 volts to the primary? So you got a 3-to-1 turns ratio. 360. Very good. What's the output voltage if an input signal is applied to the secondary of a 4-to-1 step-down transformer instead of the primary? So you're using it backwards. Instead of a step down, you're going to use it as a step up, right?
Yes.
divide it by 4. Do it backwards.
What?
Ooh.
Oh, you're
You're doing it backwards. It's 4-to-1 turns ratio, so it's 1-to-4 when you go the other way.
I thought winding is still primary and secondary.
Well, that's just nomenclature. Normally, the primary is where you normally hook it up, but if you hook it up to the other one, that's the primary. What transformer turns ratio matches an antenna's 600 ohm feed point impedance to a 50 ohm coaxial cable? So we got a 50 to 600 ohm match, which is what, 12-to-1, right? So to get a 12-to-1 impedance ratio, what's the turns ratio? It's kind of hard to do. You can do it.
Alpha.
I heard an alpha,
It's about 3.5 to 1.
Yeah.
square root of 12.
Those loops.
Huh?
Those loops that everybody always asks about.
Well, you just have to have double the amount of turns to get the, make the 3.5 7 and double the other side, so get that ratio.
I thought it's usually a 4-to-1 balance, and what it would say, you think.
Be close. Be close. Okay, we usually plot things on rectangular or Cartesian coordinate system. And, we define a point by going on the x-axis and the y-axis and then drawing that magnitude line. Or like we did for polar, we look at the angle. So, this is kind of stuff we all talk about. We use the vertical axis or the y-axis. In this case, usually the imaginary axis if we're doing impedances, reactances, and the real axis will be horizontal. Same is true for your Smith chart that you don't like. You realize the Smith chart, the guy was very intuitive. He took the coordinate rectangular system, the real axis, going from 0 to infinity. The vertical axis is the imaginary axis, so you have a plus and a minus, and one goes to plus infinity, and one goes to minus infinity. So the definition of infinity is they all meet together, right? So regardless how far you go, it's going to meet the other one and the real line out here at infinity, which means all those things eventually bend into a circle. That's why the Smith chart is round. And all of the reactance lines are curves that go back. It's actually pretty neat. But there are too many questions about it. You kind of have to know what it is. When using rectangular coordinates to graph the impedance of a circuit, what do the axes represent? So we're going to plot impedance. Impedance is resistance plus reactance, right?
This is x-axis this way. Must be Italian, so I just talk with my hands now.
Alpha sounds good. Real on the horizontal, imaginary on the vertical. Where is the impedance of a pure resistance plotted on a rectangular coordinate system? Delta. Which of the following represents pure capacitive reactance of 100 ohms in rectangular notation? So 100 ohms is the R part. Remember, it's R plus JX. So it can't be alpha or Bravo.
Gotta be Charlie.
And it's capacitive, so it's negative, right? All right. Oh, I said that.
100
I was looking.
reactance.
I messed up on that. It says it's capacitive reactance. I was thinking resistance. Yeah. So it's just a vertical up to 100 on the axis. What does the impedance 50 minus J25 represent? See what happens if you go too quick. You don't read the question.
50 ohms in series.
Baker.
25.
So we have 50 ohms resistance and 25 ohms capacitive reactance. So Baker or Bravo looks pretty good. Okay. If the impedance was 50 plus J25, then it would have been a plus JX, right? It would have gone the other way. To find impedance, we plot the inductive reactance on the y-axis, the positive side. We plot the capacitive reactance on the negative side. And then we plot the resistance on the x-axis, and we find out where that point is. Now, that doesn't quite seem the way you'd really do it, because if you've got both capacitive and inductive, I would find the inductive reactance point, and from there, measure down whatever the capacitive reactance point is. So basically, you're subtracting it. And wherever that lands is the equivalent reactance, whether it's positive or negative. If you just plot one up and one down, you still got to figure out what the difference is. Follow me?
I thought I was following until we kept talking there.
Well, okay. I mean, however you want to do it, but you have to find the equivalent reactance to plot. So you got to find the difference between the inductive and capacitive reactance. So you can subtract them before you start, or you can plot one and subtract on the graph. However, it's easier. And then when you draw the vector from 0 to that point, that's going to give you the magnitude or the length of the vector of the impedance vector. And there's an example in fact, where, and you can do the angle. So, and if we did it in polar coordinates, we're doing the magnitude and the phase angle. And you just do it on a polar plot, which is round instead of a rectangular plot. It's kind of the same thing. And a negative angle is going to be capacitive, a positive angle is going to be inductive. Now they bring in phasors, which I had a hard time finding some examples where you use these phasor diagrams. Fortunately, there's only like one question. This is an example of the polar coordinate system and how you plot the same thing we did on the rectangular. You've got a vector at an angle. This is the only real example I could find of phasors where they're showing the phase relationships or vectors between the real current and the reactive current or total current, where in this case you've got its capacity, in this case it's inductive, in this case it's resonant, so you don't have any reactive current, it's all real current. So what coordinate system is often used to display the phase angle of a circuit containing resistance, inductive and or capacitive reactance?
Maybe South Korea.
No, it's not made yet. It's not a Faraday grid either. I guess that's supposed to be a Faraday shield.
Oh, that's a rough one.
How are impedances described in polar coordinates? Phase angle and magnitude?
Yeah.
Which of the following represents a pure inductive reactance in polar coordinates? No resistance, just inductive reactance.
Oh, see,
Charlotte? Right.
Yeah.
What kind of diagram is used to show the phase relationship between impedances at a given frequency?
One you can't find examples.
Well, I have a Venn diagram.
Little bird, huh?
Near field and far field.
Well, we better go with the phaser then.
Yeah, better go with the phaser. Okay, here's some actual examples. We're going to plot. So we got a 400 ohm resistor and a 38 picofarad capacitor at 14 megahertz. So they require you to calculate the reactance and then plot it. So we know how to come over to 400, but what is the capacitive reactance?
it's negative.
Well, in this case, since we know this point, there's only one it can be.
I was going to say,
You only do one. I gotta get my calculator.
At which point in E5.1 best represents the impedance of a series circuit consisting of a 300 ohm resistor and an 18 microhenry inductor at 3.505 megahertz. So we know we go over 300, and now we have three options, 0.3, 0.8, and 0.1.
Well, the point one doesn't apply
Because it's inductive, right? So it's got to be 0.8 or 0.3. So which one is it?
I agree.
18 microhenries is pretty low,
Not very much.
so I wouldn't think the reactance, I can't do it in my head, would be that much. I would, if I was guessing, I would say 8. But I was wrong.
Yeah.
So it's more than I thought. So it's almost 400 ohms.
Wait a minute, where did they get to 396?
That's the reactance at 3.5 megahertz.
Oh, shoot, you gotta do that.
Yeah.
2 pi F L. Which point on figure E5 represents the impedance of a series circuit with a 300 ohm resistor, a 19 picofarad capacitor at 21.2 megahertz?
Don't have to calculate.
So we know it's negative. We know we're 300. So we kind of don't have
I like those.
Okay, so when we do coordinate systems, if we're doing frequency response, typically we'll use a logarithmic axis to get better looking graphs, basically, and you can cover more territory. A lot of times you'll see it on the x-axis also if you're doing a frequency sweep like bandpass filters and things. So what type of y-axis scale is most often used for graphs of circuit frequency response?
Logarithmic. It is a. Heard it somewhere. Where you have that.
Okay, so we talked about how to do series and parallel resistors, capacitors, inductors. Talked about transformers, mutual inductance, turns ratio, impedance ratios. Any questions on those?